Yes.
That's the position.
Okay.
Okay, so this is for like the homework assignment. So everything works except my problem is my end isn't working whenever I try to run it. Instead of halting the program, it gives me like an error saying there is no instruction.
You need to reformat the code. The tab may be wrong. So you can put your end to here.
Oh, okay, try that.
Yes.
Okay, thanks. I know.
Okay, let's start. So today we will talk about the interface between the assembly language and the operating system. The user code written by some assembly language invoke and ask help from the OS by the track routine and subroutine. I will introduce more in the following slides. The operating system provides function of system call for the user applications or user code to invoke some services like receive a chart from the keyboard or output some character to the monitor. So these functions can be implemented by the system call. Because these functions, these system call involve the keyboard driver, the monitor driver, so they require some specialized knowledge. And not everyone can, ask help from the operating system anytime. So you need some mechanism to do the so-called protection. Some user who really need help do the system call first. Others have a lower priority may, ask for the system call in a smaller speed, lower priority. So they need some protection. Assume that your operating system is processing some very important job. So not every user can, invoke the system call. So that's the reason why the operating system provide system call for the user code to invoke the keyboard and the monitor functions. And these I/O resources are actually shared by all the users using that operating system. So one mistake made by one user may have huge impact on the other the application of other users. So not every user understand the low-level details of keyboard. That's another reason why. So the system call is used to safely and conveniently to perform some low-level privileged IO operation, not necessarily low-level operations. For example, when one user want to use the keyboard, the other user the user program can invoke a system call, and the operating system will respond that system call, do some jobs the system call asked for, and then the operating system will return the control to the user program. So the whole process here is implemented by the trap mechanism. We have a set of service routines. They are part of the operating system. So each routine can start from a arbitrary address. Totally, we can have up to 256 routines. And we have a table to record the address of each routine. So totally, we can use either address for the routine. Sometimes this block of the addresses is called the system control block. So from this address to this address, each digit here is actually 4 bits. Then we have 2 bits here. Sorry, we have 2 digits. From this address, we have 2 digits. Each digit indicate 4 bits. Totally, we have 8 bits to represent this. Then we have 2 to 8. And in the instruction set architecture, of course, we need a trap instruction. So trap the operating system. So the trap instruction is used by the user program to transfer the control to the OS. And in each trap instruction, there is a trap. So by this AD vector, one of this after the operating system finishes its job, it will require a linkage to transfer the control back to the user program. We need a return address here. So this is the trap instruction. This is the opcode. 4 ones are the opcode. And then we have 4 zeros. The last 8 bits is used to store the trap vector. So totally, we can use this 8 bits to index system call block on the table of service routines. They are the same, different names just. So this table is actually stored from this address to this. This is also 8 bits. We have 8 bits different. And we can use the AP trap vector by some zero extending. And we can change that 8 bits into 16 bits memory address here. Because here you also have some zeros. And we just need to extend that zeros. We just need to add that zero. Attach these zeros to this bits so that we can have the entire address out there. When we have that address, we can look up this table. And then we have the routine starting address. We can put that routine starting address to the PC. So in the next instruction, we will go to that routine. The last job the user program needs to do is to store the return address to this special purpose register, which is last time. So that after the routine is done, and the user program can return this address. So here is the whole process of the entire trap instruction. When you have a trap instruction, you do the decoding, you understand how this instruction is trap instruction. You get the last 8 bits, which is you extend this function, 8 bits through. They use that to read the look up the table in memory. Okay, the table is a specifier. The table starting is after we have the starting, you look at the table, it reads the table. And gets the real routine starting address here, and then put it into the PC. So in the next iteration, in the next instruction, we will go to that. Parallel to this, there are 18 target. We also need to brief. We also need to register. So that's the reason why in the first step we also need to do this. After we understand this is a trap in instruction, we need to do 2 jobs. The first one is we need to calculate in this first step, we also need to to some specialized register, which is R7. And then we do the lookup operation in the second step. In the last step, we just write the routine starting address to the PC. So in the next instruction, we will go to that routine. So by this trap instruction, the user program transfers control to the routine. The routine belongs to the operating system. So in this way, the user program transfer the control to the operating system. So after the routine is done, we need to transfer the control back to the user program from the operating system. This can be done by a simple jump instruction. Because the return address is stored in the R7, we just need to jump to the R7. And we can use this return instruction to reference. Because this is, all the we do now to specify R7 in this function. In this case, we can just use the return function. So this is, they are equivalent. Because the R7 keeps returning around. During the routine, we cannot cancel things out. Otherwise, we will lose at the return address. Again, I will explain the when we run the user program, we meet a instruction. This instruction has the output of all four ones. Has the output of four ones. After the trap instruction. For the trap instruction, the last 8 bits. But extending aggregate zeros here. And then look at the tables. We can know the routine starting address. After we have this routine, go to the routine starting. We will go to this routine. How can we understand? How can we know this starting? We have this routine AD spectrum by extending them to zeros. These are zeros. We can get a address. We will use that address to look up this system control block in the memory. You can see that this is a free because 0, 0, 1, 1. 1, 1 is a free, and this is a 2. The 0 extending is at A to B 0 here, in from out everything. So the last 2 digits are here. One is a 2, the other one is 3. So the address is 0, 0, 26. I'm sorry, 23. We use that address to do that. And then we have this starting address. So you can convert this data address to it's a hex format. The last digit is 0. And then the second 4 bits, the second and last 4 bits is A, which is a 10. And then we have 4 here, and then we have 0. So you can see that this value is exactly the constant in that scale. After we have the routine starting address, we solve it into the PC. In next instruction, we will go to this routine. We will do the routine here. At the end of this routine, we just return. In the return, we can go back to this place in the program. So in this way, we can finish the entire operation. Basically, we do the operation, and then go to this routine, and then do the routine. 3 steps. So this is a code example of the trap instruction. the first foo instruction is used to load some character. And then we call to get the input by this trap instruction. So we need to process input by this loop. After this loop, we will display that or monitor character on the monitor. And then go back to this loop, the starting point of this loop again. Otherwise, we just finish everything. So this is the user program. In this user program, we have two traps here, and all the user program are called stop at the end of this user program. So totally, we have 3 traps here. Here is a routine for how to display a character on the monitor. So at the beginning of the routine, we do save R7. Why we want to do the save R7? Because our return address is stored in R7. We cannot destroy that address. Otherwise, we cannot return back to the user program. So for the safety, okay, we just store that the content in R7 in a safe place so that eventually we can load that database. And then we do the display. We load. So by the first store and the last load, we can guarantee that R7 all the time be return address. No. We are talking about that in structure. So for the trap instruction, we define the content of the trap vector like this these functions. This is a get a single trap table. This is the output a trap to the monitor. Write a string to the console. And turn the promote to the console and read another from the keyboard. This is stop the entire program. So saving the content of a register in the main memory can help us to guarantee the return address is not destroyed by the routine. Because eventually after the routine, we need that to the user program. So we have a goal, which is to save the user return address. Problem is that who will do this job? You have two options. The first one is the user program, the caller. Will save the content in the register to the main memory. Because the user program can know that we will need that this routine. But it doesn't know. Another option is similar to the previous example. The routine itself can do the job because the routine knows whether it change the content in the register or not. But the routine doesn't know whether this value is still required by the user program or not. Now we are talking about multiple, not only R7. The user program must require the R7 because it stores the return address. But for other, routine doesn't whether the user still require those contents or not. So here is a one example. This example is a user program. It will count the number of a char, is a specific char in a string. So at the beginning, it will load the count into this. And the char in the R6. And then you will invoke a char, that's a char from the keyboard. It will do the counting. How to do the counting? Just add some value, add this value to the value. You increase the counter. The counter is initialized to 10 for 10 times. After this counter reaches 0, it will go out of this loop. So what's the problem of this user application, user program? The problem is that it uses R7. R7 is a specialized which store the return address. What does that mean? It means that when you call this fact here, the R7, at the beginning, the R7 is the function number. But when you call this, the R7 function doesn't change because we will write return address. 7 is not a string anymore. Then if you run this program, if it keep or reduce the content, you may have some mistake here. That's the reason why we need a saving and restore the register, because the register, store the return addresses, and the register also store some data useful for the user program or the routine program. So the first option is the collect saved. Collect saved means the routine of processing. After you reach that routine, arrive in that routine, before anything start, the routine just save any registers that will be modified to the main memory. After the routine, before the return, the routine will load the original content, restore the content, and then go back to the user content. This is so-called collect save. Another option is the color save. Color save means the user before you go to any routine, the user program will save the register. Described by the following instruction. Will be described to the memory if the content in the register will be described following instruction. Otherwise, use the register so that the content in this register will not be destroyed. In that case, register anymore. The so-called saving and restore means you. So here are some questions. The first one is, can routine call another routine? The answer is yes. You can actually do it. Only if you can take care of the content in the specialized register, you can always do this. Yes, the routine also needs to store the return register address to the main memory, so that the second routine can go back to the first routine. So the routine actually have three major functions. The first one is that the routine is maintained in the system. For example, output a character on the monitor, get a chart from the keyboard. If as a user, you don't need to write the function itself. You can just invoke the trap instruction to implement these functions. And these functions will be heavily used in all the codes, and you don't need to write them again anymore. So if multiple users invoke the operating system will do the scheduling, will evaluate which user has a higher priority. So eventually all the requests will be satisfied. So there is no stopping. Otherwise, some user can initialize some attack, like it constantly asks the input from keyboard, so other user cannot use the keyboard anymore. But if you use the system call, you use the routine, you can eliminate that attack. Is there any reason to provide the same function for the non-system code, non-system code user program? The answer is yes. In your code, you can implement any function. A function has a similar characteristic as the routine. You can define a here we call that subroutine. Subroutines is actually a function. It's used in the user space. You can implement well-defined task in that function. So this function can be used by another user program. Another user program can call your function after the job of your function is done. You can return to that user program again. So this function is actually defined by users. It's not a part of the operating system. The function cannot invoke the lower. If you want to touch the keyboard or the monitor, you have to use the routine again. So the subroutine is very useful. You can, write your frequently used code into some functions so that you don't need to write them again. And you can only debug it once and then use it for future applications. You can write a function and transfer this function to other users so that other users can use your function. Or you can actually sell your function as a library. Now you can include a lot of commercial libraries in your program. You can use the function defined in those libraries in your own application. The LC3 also has some instructions supported as a subroutine. For example, this jump instruction. This is the code. It's used PC relative addressing mode. The last 11 bits is used for the PC relative addressing mode. So if here the B11, the B11 in one is the PC relative addressing. It can change if the 11 bit is 0, the target address is and this is the details for this jump instruction. In the first step, again, this is a function. This is a subroutine. First one, the first step is say your return address to our type. And then assume that this is a PC version. You get your last 11 bits. Add it to the Besides the PC relative addressing mode, we also have like another jump instruction, which is have the register addressing mode. The target address is the base register. And the feature 11 specifying addressing mode. So this address, this jump instruction is actually more powerful than the previous one because it provides some important feature, which the previous one doesn't support. Here we only have 11 bits around the PC. So we can only go to the address of a PC plus 1024. This is the range of address. This address, and I'm sorry, this instruction can jump to. But by this new jumping, go to access a larger range of the memory. Why? Because we can simply store the new in this base register. Because we only have 8 register in the LC3, so we use 3 bits to index those registers. After we know the register name, we can go to that register, and each register is 16 bits. By reading that register, we can have 16 bits address. We can go to any address in the memory. So that's the reason why the GSRR is more powerful than the previous one. So this is a per set of this jump instruction. First one is also return, save return. And then you just read this base register. It's very simple, just 2 steps. Similar to the routine, you can also use that instruction to return to the return address. And here is a function. This function is used to negate the value in R0. So this is the function itself. This is not imply a not operation of R0. And then add 1. This is so far we are completing the two's complement. The last instruction of this function is the return. So in the the main user application, if we want to compute this, if we want to compute a subclass, we actually do a addition. We just add the two's complement of this minus R3. First, we copy the value of R3 to R0. Because this function is actually performed on R0, we need to prepare our code, our data in the R0, and then call that function. How to call that function? You just use this instruction. By jump to the starting of that function, actually run this function. After we return from that function back to this main user program, we just the two's complement, the minus R3 two's complement is actually in the R0 now. You just need to, do a addition result for in this way we can complete it. Because the subroutine use R0, so if already we have some code data in R0 value following the instructions, we need to save this R0. The routine, the user program need to extend some data with the subroutines. We can pass some value to the subroutine and then receive some value from the subroutine. How can we do this? How can we do this? Passing some input can be done by the arguments. A value passed in to the subroutine is called an argument. This value is required by the subroutine to do its job. In the previous example, we need to pass this minus R3 value to the subroutine. How can we do that? We need to store this value to R0. After the subroutine is done, for the previous example, it generates the two complement minus R3. The subroutine needs to pass this value to the main user program. And this is so-called return values. This is the result generated by your subroutine. How can we pass this value to the main user program? Again, we use this R0. So in order to invoke or use this subroutine, programmer needs to know the starting its function, how to pass some arguments to that function, how to receive some return value from that function. Again, before use the subroutines, need to save all the useful data in the register, so that this value may be destroyed by the subroutine. If we do not do that, we generally use the Collie save strategy, except for the return value. So the main user program, before invoke a subroutine, will save the return and then go to that subroutine. At the beginning of the subroutine will save all the other all the other registers back to the main memory. Just before the completion of this subroutine, it will load all the values back to the and then go back to the main user program. So this is so-called a Collie save strategy. Again, no matter you use a subroutine, you have to save the So here is one example. You can write a subroutine. Name the first char to find the first occurrence of a particular char in R0 in a string. As a string will be pointed to by R1. So the return pointer to the or to the end of the string. So the R2. And then we can use the first char to write count char, which counts the number of occurrences of a particular parameter in a string, and the return count in R2 environment. So we actually can write this second subroutine first before implementing the first one. But the entire data flow will be like this. This is the count chart algorithm. This is the first subroutine. Before to this subroutine, we will say particularly R7. And then we will call the sum and go through the first chart. We will find the first chart here by this loop. Before the first chart function is done, we need to load all the records and then do the return. So here is the assembly code of that example. These instructions are used to save the content in the register. And then it will go to the first chart. So here is the first chart operation algorithm. This first chart is also implemented by loop. So at the beginning of the first chart, save all the registers to the Sept R7. The R7 is done by the count chart algorithm. So this is the assembly code of the first chart. So the subroutine is actually very useful when you your one library can contain multiple subroutines. You don't need to release your source code of your subroutine to the user. Binary machine code are good enough, and we can use assembler or linker to link the subroutine in some library to your own code. So here is some example. You can invoke some sort operation function or subroutine provided by some libraries. By clear, this is external subroutine. And for the external subroutine, we prefer this JSS instruction because This subroutine may not be 1,000 instruction of your current PC. Any question about routine and subroutine? Yes, they have a 3Ds, 3Ds in this instruction. It's classified as H register. After you have that 3Ds, you can know your base register among 8 registers, and then you can read that. This is the starting. Any other question? I think you can try at least routine. You can call a routine to receive some input from the keyboard. Or I post an assignment of your project. You can choose a project topic which is close to your own research, or you can also propose your own research topic. We will do a presentation, which is a so-called project proposal in the following weeks. You can check the data on our syllabus. And in that presentation, we can discuss whether this is a whether you have a large enough workload for the project. I prefer you have a very concrete topic. Even a small project, I believe that's a very good enough for one person project. Based on my experience, some students prefer to select a very large topic, which you cannot, complete within one semester. For example, you can implement some adder or multiplier by Verilog Verilog code. You can implement some hardware adder or multiplier. Or you can write some program by the assembly or C language. If you have any questions about that, otherwise we can stop today. Thank you very much.
I have one question regarding assignment.
Yeah.
So, in time, actually, consider the tree. So, the one we need to decide. So, there were two numbers provided. So, I assume these are the signs for them.
Yes.
So, these were the numbers 9, 3, or 4. What they were taking say. So,
This is for 2.
this is I sign and that one is
Yes. Yes.
These two numbers, this one should be the original. Because
You cannot guarantee the second one is allowed. Yes. Yes.
So in that case,
Yes. Yeah. Yeah, after you present all the evidence, yeah.
said professional method and
Yes.
so it has to be, so I guess my teaching is